Sorry everyone for the technical delay. Today we're very happy to welcome Tamar from Weizmann University. Tamar is professor for applied mathematics and computer science in Weizmann, and she's working on motor control in biology and robotics, and in particular the computational aspects of it. Computational aspect of it, and in the lab they study how information processing, control theory, and applies to learning and training of motor commands. Today we'll hear about control principles in motion generation, and she talked about motor planning and how can be understood through optimal control theory and through geometrical symmetries, and how this perspective will help us understand neural representation of motor control. We'll also discuss how complex movement can be described by simple motor models. Thank you for being with us. Sorry for the technical problems.
Nice to be here. I haven't been here a long time. Definitely not in this new, amazing building. I see a lot of the recognized faces in the groups physically. So I decided not to give a very deep technical talk about each specific topic, but try to give an overview of and the connection between different studies. So these are the questions I'm interested in, and they are about principles of motor control, but also how they relate to perception of motion, and also to the geometry that subserves our motor production and perception. So, okay, so when we talk about movement or motor control, there's grand questions that, of course, I won't be able to answer, but the research I've been doing are trying to understand some of these aspects. So first of all, we want to ask what is the hierarchical organization of the motor system. Secondly, what control principles and strategies underline certain behaviors. Of course, don't study all actions. I focus a lot on arm movement and locomotion, and whether and how movements, complicated movements or action are built from a more elementary building blocks, like what we call motor primitive or motor units. And I try to answer or to have some light on these questions. Now, when we talk about motor control, we have to have an interface between information and physics. It's all obvious. And the nervous system has to deal with lots of questions that actually in robotics too, when researchers build robots, you have to address questions like physical variables, namely kinematic variables like position, velocity, and acceleration, but you have to generate them through forces or torques, which are the aspects of dynamics. I mean dynamics not in the sense of temporal, but more about the generation kinetics, what we call. And of course, we shouldn't neglect time, because we believe that there is a lot of intermingling between space and time variables. So I want to pay tribute also to the famous Nikolai Bernstein, who was a pioneer in the area of motor control. Not too many people knew about him. He was in Russia, and Stalin didn't allow him to work for 12 years, and he was discovered rather later on in the West. But he claimed that there exists in the higher levels of the central nervous system projection of space and time. Also, he didn't say time, but projection of space, and not necessarily projection of joint and muscles. These might be dealt with at lower level of the motor hierarchy and not at the higher level of the motor system. So evidence for this notion comes from all the, this was actually I found in the thesis of Mike Rayburn, who was later built the Boston Dynamics company, but originally he was at MIT, and he had an example of how we write the word coordination. That's taken from Bernstein in Russian, and it doesn't matter if we write it with a little on a piece of paper and we write it with a pen, like number 1 and 2, or maybe if we write it with a pen sticking to the elbow, or even with our leg. Because the question of kinematics, spatial traces of time, are the same, and the brain has this invariance that in space and time, not necessarily taking into account the dynamics. So early on, I know some friends of here may have seen that already, but I'm starting there. So this is all work done in the laboratory of Emilio Bizzi, but Eben and Morasso, they asked simple question. When I want to move a manipulando from some initial position to one of 6 targets, what kind of trajectories do I do? And you always see straight line trajectories, and the velocity are bell-shaped, almost symmetric, with one peak. But when I do that with my arm, I have to move the different joints differently in different parts of the workspace. That means that I represent in the brain, maybe higher level, just the kinematics of the movement itself. But when I do a curve trajectory, that here, that movement that goes through several peak of curvatures, I don't no longer have this nice bell-shaped velocity profile, but I have these different shapes of velocity which are coupled to the maximum of curvature. So every time I go to a maximum of curvature, I slow down. And you see it already in babies, at a small age, young age, but you also see it in animals, and this is very interesting phenomenon. So really years ago, together with Neville Hogan, we said, what is accounted for this kind of behavior? Neville, MIT, he suggested the principle of smoothness, which is expressed in terms of the jerk. Jerk being the rate of change of acceleration, but we don't look at the jerk at the joints, but we look at the jerk at the end effector, what the hammock is doing in space, and we look at the integration in time, and we assume that the brain wants to do the maximally smooth movements in some duration. We can talk about duration later. And when you take this model and predict behavior, you can see that the velocity profile is this smooth bell-shaped velocity profile, which are fifth-order polynomial. The path is straight line, but if I just subscribe one via point that I want to go through, you get this velocity profile of the hand, which has 2 humps. This is maximum curvature, so I slow down at points of maximum curvature, and the model is good enough also to predict the duration of each of the segments. It's not something that I prescribe, it comes from the modeling of smoothness. Okay? So this is an early attempt to look at the minimum jerk model, maximum smoothness, and we then really took it a long way. We model it many different kind of behavior, and people have looked at it in babies and other in development. Now there's another group of models developed by Laquaniti, Tazzuolo, and Viviani in Italy, and they looked how the velocity changes again with the curvature. So velocity is proportional to the radius of curvature to the power 1/3, or if you look at angular velocity, velocity is proportional to the curvature to the power 2/3, and k is of some constant, which is piecewise constant gain factor. We call it piecewise constant gain factor. So if you plot log v versus log r, you see that there is segments that are straight, which have a certain slope, which is the exponent, and you can generalize it to complicated trajectories like that. So now what it says actually is that if I'm drawing an ellipse, I always slow down at the parts which are more curved. So this is, we all do it, babies do it, children do it, and there is this coupling, very nice coupling between velocity and curvature, which a priori shouldn't be there. Why does it happen? So later on, work was done in different labs. For example, it was done in the laboratory of Berthoz, Alain Berthoz. They looked at people walking in shapes that looks like double ellipse, okay? And when I walk along double ellipse, You also have this ratio between, just ellipse. You have this log power law with similar exponents. That means that I have the same kind of plan regardless if I do it with my hand or if I do it with my center of mass. This is trajectory of the center of mass. Okay? So says that the brain has the same kind of geometrical principles regardless of which kind of action I do. You have now two kind of models. You have this idea of smoothness, and you have this idea of power laws, exponents. I didn't say that the exponent for ellipse is 1/3, but it doesn't mean that all shapes that I'm drawing with my hand when I do drawing movements is 1/3. Okay, we get it. So a long time ago with my postdoc, Magnus Richardson, we said, okay, why jerks? So maybe we can minimize minimum acceleration or minimum snap, which is a higher derivative, is third order derivative of position. Okay, so it's 1 above jerk. And you again can use mathematics to model it. The way Magnus modeled it, he took integral of the derivatives with respect to time, but he went all the way to n, very high n. He started with a perturbation analysis of the trajectories, and he could predict the betas, this exponent, for different kind of shapes. So it's actually, this is the results. It's a paper was published a long time ago, 2002, and you get that qualitatively it's very similar to what we saw before, relationship between log and P and log radius of curvature has this piecewise segments with constant slope for the different segments. So that's, but you minimize the cost for the entire trajectory, not for piecewise. So a priori it says that the brain doesn't have a segmented planning for something complicated, but actually you may have a planning for the entire trajectory, and segments come out from this kind of principle. So that's very nice, but I actually wanted to go along a different tour direction and ask what kind of geometry does the brain use to represent motions? Because we talked about jerk in the Euclidean space, okay? And we know that in physics there's a lot of development for 100 years or more looking at the physics from the aspect of geometry. So maybe this is a suitable kind of direction to go also for neuroscience. So this is tightly linked to the theories of groups. And now I'm talking about the hierarchical organization of groups. So you have different groups of motion. You can go for motion that are Euclidean, namely you preserve the distance, Euclidean distance between the regular geometry that we know, and it preserves angles. But this is the most restricted kind of geometry. What happens if we want to loosen up, for example, the representation, the conservation of angles? Okay, so you have to go to affine geometry, and above this is the projective geometry, and above this is topology. So you have this group of motion that you can represent with matrices, but this is what Felix Klein was talking about when he talked about the Erlangen program, which is this hierarchy of groups that are not necessarily only for motor control, they are also applying to perception, for vision or haptics or whatever. Okay? So as I said, you have group of transformation. Euclidean preserve translation and rotation and preserve angles. Then you have the affine, which preserve translation, rotation, stretching, and dilatation. It just preserve, incidence and parallelism between line. And subgroup of affine is equiaffine that also conserves area. So why I'm bothered to actually look at all this mathematics or geometry? Because if you look at the 2/3 power law or 1/3 power law, you can define a new kind of distance, equiaffine distance, which is taking into account not only ds, this is the distance in Euclidean geometry, but it's weighted by curvature to the power 1/3. Okay? So this is not my invention. It's known geometry. It's called equiaffine geometry. But this gives exactly the behavior that you slow down if you do an ellipse along curved trajectories. If you move at a constant equiaffine velocity. Okay? So if you move at a constant equiaffine velocity, you slow down exactly as we see the behavior. So I just want to, on a side, to say that in vision, there's a lot of people who have studied visual psychophysics, like Todd and other people, and they also emphasize the representation in terms of affine and equiaffine geometry. Now this led to the use of what we call moving frames. So in mathematics and geometry, there's a notion of moving frames that was developed by Eli Cartan. So if I'm moving, okay, I'm moving like a dot in a plane, and I have a coordinate system attached to me. Now the coordinate system need not be Cartesian, okay? In Euclidean geometry, we have Cartesian coordinate system. But you can have a coordinate system that between the tangent direction, which is pointing in the velocity direction, and the transverse, you don't necessarily have a 90 degrees angles. So this is exactly moving frame, okay? So in Euclidean geometry, this is the tangent, this is the direction of velocity, this is the transverse. But the equiaffine, and you can express the transformation between the group via the curvature, Euclidean curvature. But you can move to equiaffine geometry, and then the angles between the tangent and the transverse is not 90 degrees, it can be different angles. What that preserves is just a parallelogram between the transverse and the normal, and I preserve the area of this system, of this parameter. So equiaffine distance is actually a measure of area, not a measure of distance, it's a measure of area. Okay? So this applies here too. If I take a trapezoid, I stretch it, I just preserve the parallel line to be parallel, I get a new kind of trapeze. But if I want to be invariant under equiaffine, I just have to preserve the area of the trapeze. Okay? So, so this is just mathematically, you can express here. This is the equiaffine distance, which is the curvature, Euclidean curvature to the power 1/3 times the Euclidean distance. So if I do the sigma to dt to the time, this is piecewise constant. Okay? So now can I use it to describe trajectory in humans? I just want to say that there's, I'm sorry, I may be losing some of you, but the same way that you have curvature in Euclidean geometry, which we know that straight line is a constant curvature, a zero curvature, circle is a constant curvature. We also have a measure which is called equiaffine curvature, okay? And it can be constant, it can be for ellipse, it's positive constant. For hyperbola, it's negative constant. And for our parabola, it's zero, okay? So this is just showing here. And when I use this kind of measure, and I looked at human velocity, human movements, I see that this complicated trajectory has a constant equiaffine velocity along it, okay? So I can generate very complicated trajectory with having a constant equiaffine velocity. And if I can go to a 3D kind of motion, if I do movements in 3D, I have a curvature, velocity, and torsion, which is the plane of the 3D movement. And if I want a constant equiaffine velocity in 3D, I get a new law, which says that the movement of people should be obeying this kind of law. We also actually tested it, and it was really validated in human trajectories. Okay? So now it's all very good, But the problem is that I have not accounted for the duration of movements, because the equiaffine is a local loop. But if I look at trajectory that I do a big ellipse and a small ellipse, I do it roughly the same time. That's how we all do it, okay? Or if I plot a double ellipse, I do the big ellipse and the small ellipse also at the same time, okay? It's very robust. So this law of equiaffine is not enough to account for this duration. So that's why we have to go to a higher kind of geometrical explanation, which talks about affine, not equiaffine, which preserve area, but affine, which is called the general affine. And then we assume that a total affine velocity is constant. That means that the distance, affine distance, is equal to the total duration. Okay? And if I am operating that under constant affine velocity, I'll have the same duration for different kind of trajectories. That's actually what you see here. So this is called the isochrony. And what we say, what does it imply with respect to time? It says that movement have a constant affine velocity. The time is proportional to the affine distance. Okay? And time depends on the geometry we use to measure distance and represent movement and velocity. Okay, so we then took it to another kind of model together with Daniel Belican from Paris. We assume that you have the three geometries. You can also go to projective geometry, but you have a velocity that is dictated by this mixture of velocities. You don't have just one principle. And it also says that we don't have neurons that just encode for one kind of geometry, but they encode for the different kind of velocities. Okay? So you have a multiplication, you have this constant velocity in the three geometries, and you have a general principle, okay, which says that I have the three geometries. Each one of them is represented by different kind of curvature, and I have weights and different weights for the different geometries, and we try to model with these complicated movements. I will skip the part about singularity but it's important because if I'm drawing something and curvature is 0, I have an inflection points. Okay? So how do I deal with inflection points? And therefore, but I'll skip it. And we use this model, the mixture, to model both locomotion and drawing movements. We assume you have the same three velocities, but you have different weights for the same velocities. You can then segment the trajectory and model the different segments. And we looked at different kind of shapes, and you assume that within each segment, you have the three geometries have each one of them a constant weight, constant gain. So with this, we can model complicated trajectories, and we can predict the kind of segments that we get. And also we can predict what happens in locomotion versus what happens in drawing. And indeed, we found that in drawing, you have most dominant are the Euclidean and the equiaffine. And in locomotion, you have the Euclidean and a little bit the equiaffine. Okay, so you have different tasks with different mixtures of population of same population of neurons. That's our hypothesis. And also you can predict, as I said, the total duration that you have spent when you do kind of movement like this. You have different duration for the small ellipse and the big ellipse, and the duration relationship is predicted by this kind of law. So this is what people are doing. The solid time and the dots are the actual experimental data. Now, so let me leave it with this. One more thing. We wanted to see how whether we can use the same principle for perception of motion, not only production of motion. So this starts with a study that was done by Vivian and Zolzuolo and Vivian and Stuckey. What happens if I look at the screen and you have to change the law of velocity, this kind of law. And you ask people to push buttons and to say, when does the movement look most uniform? And apparently, it seems to them most uniform when beta is indeed 1/3, which means that if the movements obey this kind of 1/3 power law, the motion looks more uniform.
How do you define uniform in what sense?
We didn't mention anything. We say, when does the motion looks more not natural but uniform?
But did you see that does it mean the velocity is constant or just this?
We give it to them and we say, you push the buttons and you choose
Okay.
when the motion.
No, but now you can say go back to the values they took and see how do they define uniformity across people.
So it wasn't my work, but a lot of people ask also the question, how does the motion look more natural? Okay? And a lot of people really chose the exponents that we produce the movement. They also use it for, okay? Now, very interesting, I'm not showing the results, but we test it also in autistic children, for example. In autistic children, healthy subjects use beta 1/3. In autistic children, you are very much closer to being constant velocity Euclidean. Beta is 0. Okay? And but I don't show the results here. Now we did ask, this I don't have the movie to show you, but we did put the people in the magnet, okay, and ask them, just look at the dots, and we have the dots moving in different kind of velocities, and see what part of the brain are active, okay? And we saw that when you have a 1/3 power law, the natural way for ellipsis, for example, you get a huge or big network of motor areas, including the mirror neurons, the motor cortex, the PLB, the cerebellum, and the basal ganglia that respond more strongly to the natural laws of motion. Okay? Not only visual, but you have very few areas only in the parahippocampus that really like the constant velocity, which means that it's not the visual areas; these are motor areas. Okay. So actually, we continue doing studies that I didn't have time to talk about it. Studying, for example, Parkinsonian patients or autistic. We didn't do study in autistic using fMRI, but we did study with EEG. Okay, and we saw that if we look at the activity of the EEG, you get what we call mu suppression. You know about mu suppression? Mu suppression is the suppression of EEG waves in the beta band, or the lower, a mu band, which is 13 hertz, and you get the activity in the 13 hertz is more suppressed before you see a motion, or during looking at motion that obeys the power law. Okay, so we have a lot of evidence that not only mathematical, but super activities, that there are networks that refer this kind of laws of motion. By the way, there was a study that done by, this is also what I said about the EEG. So we have people looking at the EEG, different kind of laws of motion, one time constant velocity, one time this is the yellow, the 2/3 power law, etc. And this is the mu suppression results. So you see the activity, and you see the mu suppression. The power in the mu band, and you see that there is a real suppression when you have a 1/3 power. Okay? Now, nowadays we actually also, I'm working with a student that actually uses a neural recording within the motor cortex and in the basal ganglia. And we're looking if there is an explicit encoding of the affine velocity and affine velocity, in addition maybe to Euclidean velocity. And we actually started to get the positive results, so I think it's interesting. Now, how are we doing with time? Any questions?
45 minutes.
Sorry?
45 minutes. Good question.
More 45?
25.
25, okay. Now, these are all questions but they don't talk about the actual execution of the movements. Now, there is a lot of work done in motor control trying to find the modules and the blocks of action that are important in the execution of movements. So for a long time, I've been very interested in the question of compositionality, namely that you have primitives, or what we call motor primitives, and I believe that you have motor primitives not at the level of only of kinematics, but also at the level of execution, mainly the level of muscles, because we know that you have muscle synergies, and also the level of joint motion. So, okay, maybe I'll skip it. Maybe if I have time, I'll go back to this mathematical stuff too. But I'll skip it for now. So what are the principles of transforming the motion, for example, of the leg to the motion of the joints? How does the brain do this kind of coordination between different effectors, different segments? So actually, this is work from Weizmann. They look at the joint angles when they vary for the lower leg when you walk. And if you look at that, you have 2 degrees of freedom of the feet in the plane, but you have 3 degrees of freedom for the joints. You have the hip, knee, and ankle, okay? So the question, how they vary with respect of each other, and how does the brain, if I move, if I draw, okay, I have this end effector motion, but I have to move the joints. So how does the system resolve what we call inverse kinematics when you have extra degrees of freedom? So actually, Weizmann and Ivanenko, they found that if you plot the 3 angles of the joints when we walk, you have a plane. That means that you have reduced the number of degrees of freedom by 1. Okay? So you always constrain to be, this is plotting joint coordinates. It's not in a, they should have plotted it as a torus actually. But if you plot it in the plane, you get a flat plane, and you have a very typical shape, what we call T-drop shape, that is what we get in healthy subjects. Now the question is, how can we explain it? So what we did was a very simple model. We assumed that each joint is moving like a simple oscillator. Okay, we can have a higher harmonics, but for now, let's look at simple oscillator. But all the 3 degrees of freedom, hip, knee, and foot, have the same kind of frequency with some kind of phase shift, okay? And if you do that, you can say, okay, so how do I get this kind of shape, eardrop shape? It's actually more closer to the ellipse, and I get it if I have a phase shift between the different joints. Okay, so this is a very simple model, but we can really predict the direction of the unit vector, which is normal to the plane. Okay, so this is the mathematical expression. You have phase shift between the different joints, and you can take this to describe the shank and thigh and foot for locomotion, healthy locomotion. The question is, what happens in different diseases? In Parkinson's, for example, or in cerebellar patients. So actually, in Parkinson's, we have a very similar kind of description, and you have this planarity is preserved, but in cerebellar patients, this time shift, it's actually time shift because it feels like a phase shift, but this time shift is really disturbed. And therefore, you get a kind of deviation for this kind of shape, and this can account for the behavior we see in Parkinson's patients. Now, recently, we also use the same kind of model to describe complicated three-dimensional trajectory in the arm. So again, for the arm, I have 3 degrees of freedom of the shoulder and 1 degree of the elbow. If I don't, I restrain the wrist. And therefore, the question is, can I do the same kind of analysis to have this kind of constraints? So the question is, which kind of coordinate system to use? So we use the coordinate system which it talks about 2 elevation angles for the shoulder and the elbow, and two azimuth angles. And when you do that, this is the coordinate system, we can describe, decompose the movement into, it's not a PCA, it's called a coed mixture. We have a paper on that. But what was interesting in these results is that if we use this kind of decomposition, we get the same kind of sources, okay? The sources, the basis temporal features for all joints and for the end effector, okay? So you can decompose the movement of the end effector, the XYZ of the end effector, and each one of the joints using the same kind of sources, which means that I can go back and forth, inverse kinematics or forward kinematic, just using the same kind of sources. So the sources would be the elements from which I do coordination, and therefore I get this kind of plane. And we get also constraints here. So it will be very interesting to see if there is something in the spinal cord or also in the cerebellum that really constrains this kind of organization into these sources, oscillator, simple oscillator. Now, just one more topic, quickly, and this is the work of Naama Kadmon, David Ungarish, and what we did was we took the data from Katsopoulos, and the neural firing of the cells, and we wanted to see, again, what are the primitives that underlie the continuous movements drawn by monkeys. The data is the motor cortex. This time they used the hidden Markov model, and they looked at trajectories. Either you're doing a point-to-point movement or you do what they call target pursuit movement, okay? And using H&M, they decoded the neural activity. They didn't decode the trajectory, they decoded the neural activity. And from the neural activity, they asked what kind of components or kinematic components do we get. And so they found that you have states, okay? You have states. And then they can look at the trajectory themselves and see what the segments or the states correspond to. And this state corresponds to half the velocity profile from initiation to the middle to maximum curvature. And then they looked at kind of the composition. And so they get, they look at the population vector, and they can do encoding of trajectory in terms of acceleration and the acceleration direction, both direction and acceleration.
But you have both, when you have an increase of speed, it depends on where it is in the space. You see, you have green and purple are the same speed change, okay, the same direction of speed.
Yeah.
But it's as I understand it, it's in different positions in space.
Yeah, so the position doesn't matter. So what it says actually is that you have these patterns that are very similar, regardless of where you start with M. Proposition. And then you have this velocity coding of trajectories. Okay, so the states are called in the direction of velocity, which is the tangent, what we talked about before, which is the tangent, and the peak of velocity. But actually, you can look also at acceleration. So we are still, I'll show you in a minute. So if you look at single cell, you see that these are points where you have the transition between the segments. Even single cell obey the same kind of segmentation. Okay? Now, I'm not totally happy just with this because it doesn't fall into the picture and how you do a more complicated sequences. Okay? And how does it relate to the geometrical description? Because this may be a very low-level kind of units that you have to have a build hierarchy of units. So how you do sequences, you might build it from these simple segments, but then you have laws or regularities that obey something like having a constant equifying velocity. Okay? So this does not necessarily be done at the motor cortex. It could be done by the basal ganglia, or it could be done by the cerebellum.
I don't believe so. I believe if you do the analysis from some other angle on the same group of cells that you have, you will see both. Because you see, when you reach, in all cases, when you were in different part of the space, you were in different
Okay, so yeah, I see what you're saying.
context of the movement.
Actually, you are, yeah, so maybe you have some kind of lateral connection within the cortex that will give you sequences, that then you have the principles of kind of keeping the duration constant or encoding it, but gets in, yeah, you're right, maybe, yeah. Okay, but I think the basal ganglia also definitely plays a role. Because if you look at if you look at movements of human subjects, you break the movements into sub-movements. So they're no longer smooth, okay, like in healthy subjects. Okay?
Yes.
So some of the phenomena is not all sitting in the motor cortex. Okay. Okay.
You're right, but
Yeah. Okay, so finally, I talked about a lot of topics, maybe too many, but recently I became interested in the. So this is just summary of what I've said, that you have invariance in terms of scale, time, and velocity. And the question that I'm now tackling is the question whether you have scale invariance also for space and time. These are another question. We have all this fMRI and EEG studies that support some of the stories about kinematic regularities. We also did some imagery studies. And now I've been, maybe I'm a religious professor now, so I can study other things which I'm interested in the arts actually. So the question is, whether you bring this principle to things like music and dance and visual arts, maybe you have the same kind of language and the same kind of principle that also apply to building a static behavior, and maybe this, we can use it to analyze things like music or dance with the same kind of non-Euclidean geometries and these ideas of smoothness. So we actually had a symposium in Paris with Alain Berthoz, and we talked about space-time geometries in motion and perception in the brain with the arts. This was an edited book with lots of people participating. So of course, this work done with many, many people throughout the years. So a lot of my colleagues and my Emilio Bizzi, Neville Hogan, Alain Berthoz, Moshe Abeles, Nikos, Martin Gilzer, Polik, Daniel Benekem, with whom I did the geometry, and many students and postdoc. So thank you. Questions?
Yeah. So I think it's a very general question. So modern studies of the motor cortex actually emphasize the motor cortex as being a dynamical system that generates patterns. How do you relate between those?
Yeah, I think it's the same thing, basically, because I don't think the dynamical system is just a mathematical description of space-time relationship. Okay, I know the work of Shinoy, and I know their, what's his name? Okay. Churchland. But I don't see it differently, actually, because I didn't show you this kind of piece of work, but we do look about motion as being orbits, what we call unimodular groups, or unimodal groups that can be Euclidean or could be equiaffine and affine, and they generate primitives.
But is there any way to connect, like to set predictions based on the one model?
I think what we do, in a sense, is because we, I believe the velocity is coded, okay? Of course, you have to also position velocity is coded. You have this equation, because when we talk, you have this differential equation. So if you have a moving frame, okay, you have to move the frame along a path, for example, okay? So I think the dynamical system is one way of description, is another way of description. The question is not so much the mathematical machinery to describe it, but what kind of organization principle or invariance it brings out. So I think I saw what they do, and I think the invariants we find in movement are, I didn't talk about it, it's work by Yaron Meirovich. It's the idea of orbits. And orbits, they have these unimodular groups, and they are not anything, they are very specific. So you may have ellipses, I didn't have represented, maybe you have conics, and you have logarithmic spirals, and these are the type of primitives that our system generates. They are not anything, they are very particular ones. Yeah.
So things related to that question. Let's say you run an experiment, you have an arm, called neurons, you repeat it many times and allocate the activity of the population. So you get a smooth trajectory. Do you think that the smooth trajectory of the neural activity will have the same?
Yeah, actually, I think if you, that's something that I'm actually working, but if you look at the population vector, you believe what some people like John Joker say. So the population vector behaves like the velocity vector of the population. Okay? And so I think that the something like minimum jerk, you can write it in terms of the population vector. Okay? So to be smooth, if you're expressing the population vector, you get the dynamical system that gives you smooth trajectories. See? But these things are under certain constraint. For example, this equiaffine thing or fine, you have a constraint of the area. So having a constant equiaffine velocity is having a constraint on the area. Okay? So it's like some sort of Kepler's law. Okay? It's some sort of Kepler's law, not necessarily in position like center force field, but higher derivatives.
But do you have a way to write it down in the first order dynamic?
Not first. You have to go to the third order.
So
Yeah, you have to go to the
dynamic
third order.
is first order, so it's about the productivity of the network.
Yeah. You can write it in terms of a third order dynamics. I think that's what the jerk is.
Yeah.
Okay, so I think if you write the third order dynamics and you express it with this new kind of variables like affine and equiaffine, you get a dynamical system in terms of equiaffine and affine variables. Okay? And you can maybe account for the population vector behavior and stuff. Okay? That's my...
There is something that is still for many years, and it's like naive something. The time constant of changes of neuronal activity is much faster than the changes of the muscle synergies. It takes time for the muscles to make changes, right? So the dynamics of the muscle is slow.
Yeah.
If the dynamics of the muscle is slower, why should I go if I want to compute the end of the arm? You say you have to go to the third order. And in fact, you go there for reasons that have to do with the smoothness of the...
So this is the old question.
And the smoothness is slow.
So I have a question. I have an answer, okay? This is why I went to the fMRI, okay? Because when you do fMRI, you don't have muscles. You get motion, okay? And you don't have muscles.
Yeah, but fMRI is also a low-pass filter, so it's hard to know. You don't get the dynamics of the neurons when you do fMRI. But from Patsopoulos' work, you can see the dynamics of the population vector in a short, high resolution of time.
But you have...
I agree with you.
No.
If you look at the population vector, just like you just answered, you get very nice, smooth trajectory. It's the average of activity of many cells, and it gives you nice smooth trajectory. What I don't understand is the issue of the smoothness as a result of minimal jerk. So what the system is trying to do is to create smoother movement from noisy.
Babies,
They don't have the.
wait, babies, when they start to move, they do movement like
Yeah,
this,
they
okay?
don't know to do this.
But little by
Even
little,
to the age of 3.
okay, but little by little, when they develop, you get a smooth kind of
What do
projection.
they learn to organize their neural activity?
No, I think what you have is also you have this lateral connection and moving waves that will go across columns. It's not, it's not the single cell that build the picture. It's an orchestra. So you have, and you have also the basal ganglia with its time constants, and the cerebellum. So all this comes out as an orchestra from this. The muscles don't they do what you don't project with the.
Yes, I can tell you what happens. What happens is the prediction of the results of the organization that you create is what you learn. You learn to predict the consequence of your
But something
neural
smooth,
encoding.
but something
The
smooth is more
smoothness. You learn
predictive.
to know if what I'm going to do will later be smooth.
Yeah, but that's more like it's also good for prediction because it doesn't jump. If I see a tennis ball coming, okay, or if somebody is hitting a ball, I can predict where this trajectory will go. Or when I'm a football, what do you call it, a gatekeeper.
But your equations are constant. They don't change, right?
No, of course they change. The minimum jerk is an integral. But then you get you get the third order equation or sixth order equation, which are differential equations. Okay, so you get solutions which are sixth order or fifth order polynomials in time. Okay, but you can segment them, of course. That's what the segmentation is. Okay, so you see, so the time machinery brings these segments which are polynomials in time or something similar. Okay.
Any more questions?
Yeah. Do you have an intuition why 1/3 is particularly beneficial as an exponent for the movement? Is it somehow easier for the muscles in terms of curvature? It's hard to say, probably. Yeah.
It's because it's very much dependent on geometry. Okay, so there's a work by Sijnovsky, Ewan Sijnovsky, a paper in PNAS in 2015, when they also predicted trajectory that, and they predict the beta, the 1/3 or whatever, from the spatial frequency of the trajectory. Okay, so if you have a closed periodic curve and you have several maxima, you can predict the kind of exponent. Okay, so if I plot a logarithmic spirality, it will be at 2/3. Actually, they predicted 2/3. We don't get so much 2/3, so there's something more complicated. But also you have feedback, so it's getting messy.
Okay, thanks.